We move into the indefinite integral, and I want to start with just a little piece of the fundamental theorem of calculus. And if you think it sounds important, it is. The fundamental theorem of calculus, sometimes I will abbreviate it as FTC, the fundamental theorem of calculus. And of course, we know it's called fundamental because calculus is so fun. So Isaac Newton, in his great discovery of the calculus, he actually discovered the relationship between integrals and derivatives at the same time. Yes, the man was brilliant. He discovered, watch carefully, that if I take the derivative of the integral of a function, that I just get the function. This is just a little piece of the fundamental theorem of calculus, which we will talk about in greater detail before too long. The idea, here is that if I integrate, we've been talking about this integral symbol. If I integrate a function, I can go backwards, all right? So the idea is that integrating is going backwards from differentiation. And if you look at that statement that I wrote from the fundamental theorem of calculus, that's basically saying that. If I take the derivative of the integral, I wind up back where I started, okay? And so we're going to see how this works, and we're going to learn how to find, and what these things are called are antiderivatives, as we're going to see here in just a minute. We've been working the last week or so with the definite integral. Okay, we've been working with the definite integral, where we have some limits of integration like 3 to 7 of some function. And, we look at that function, whatever it is. We've been doing a lot of linears. Maybe it's a linear like that. And if I want to do the integral of that, I go from 3 to 7. All the stuff we've been doing this week. And I calculate that using an area. That is a definite integral, all right, because it has limits of integration. So, if I have an indefinite integral, and I talked about this a little bit the other day, if I have an indefinite integral, it is just the integral of f of x dx, and there are no limits of integration. Okay, that's the big thing. No limits of integration. All right. So what does it give us? Well, do you remember taking the derivative gives me the general slope function? Well, finding the indefinite integral gives me, I guess we could call it a general area function. A general area function. okay, that I can use to find the area under the curve anywhere. All right? So, when we did the general slope function, if I did, let's recall something here. If I were to find the derivative of 3x squared, that's an easy one. It is 6x. Well, we said that is a general slope function. And I could find the slope of the tangent line anywhere. All right? If I wanted to find the slope of the tangent line, slope of the tangent at x equals -3, okay, then all I have to do is put that -3 into the slope function and it will tell me the slope of the tangent line. Well, now we're going to be, for example, f prime of -3 would be 6 times -3. It'd be -18, for example. All right? But if you remember, let's go backwards. If you remember in your notes, do you remember the very first long area problem we did? Remember when we looked at, let's again consider our old friend f of x equals x squared. And do you remember when we did that really forever long problem and we went from 0 to 3 and we broke it up into all those rectangles, right? Remember doing that? And then we added up all of the areas, all 12 of them. If you look back in your notes, and I suppose somebody can if you want to, what area did we get on that problem? What was the area of that region? Do you remember? And I think it wound up being actually 8.98, right? If you divide it out. Okay? No, 1 over 256 was the very first rectangle.
Yeah, it was 8.98.
8.98 was our total area of that region. All right? Well, watch what happens here. I'm going to give you a little clue for how this can work with an antiderivative. If I wanted to do the integral from 0 to 3 of x squared dx, remember, this is x squared. Okay? Well, we go backwards and we find the antiderivative of it. The antiderivative of this is 1/3 x cubed. Now let's think through, and I'm going to show you how to get there in just a minute, so just relax. I'm going to show you how to find that antiderivative in a minute. But let's think of that for a minute. If I were to do the derivative of this, wouldn't I get x squared? Right? If I were to do the derivative of 1/3 x cubed, it would be x squared. Right? So what we did was we went backwards. All right? This is called the antiderivative. What I'm doing here is I'm showing you the point of finding the antiderivative real quick. So watch. What were my limits of integration, everybody? 0 and 3. I want to show you how this antiderivative is really cool. If I put this 3 in for x, I have 1/3 times 3 cubed. And then I subtract what I get when I plug the 0 in. 1/3 times 0 cubed, I get the exact area under the curve. What's 3 cubed? Isn't it 27? What's 1/3 times 27? This thing over here is going to be 0. Isn't it 9? Remember this number? Ooh, pretty cool, isn't it? The exact answer was 9. The exact area was 9. We estimated the area, and we did a pretty darn good job that day and found out that it was 8.98. Finding the antiderivative and then plugging in the limits of integration will give me an exact area. And that's the whole point for finding an antiderivative. All right? What we're going to do first, though, is we have to first find out the skill of finding an antiderivative. So that's what we're going to accomplish today. Let's get rolling. Let's do some examples. Let's find the antiderivative of x to the 4th. And do you remember your derivative table that I gave you? Well, there's also an integral table on there. As a matter of fact, I'm going to pause the video and let you get that out. So now you have your integral table out. And if I'm finding the antiderivative of x to the 4th, I'm essentially still just finding the integral of it, and it can be written this way. All right? So if you see the integral symbol and x to the 4th dx and you don't see any limits of integration, you're just going to find the antiderivative. Now watch how easy this is. If it is just a regular old single term like this, x to the 4th, all you have to do is add 1 to this number, x to the 5th, and then you multiply it by 1 over that 5. And that is the antiderivative of x to the 4th. 1/5 x to the 5th. My equal sign kind of got in the way there. 1/5 x to the 5th. On your integral table, you will see this statement. This is kind of like the power rule backwards. You will see this. The integral of u to the n du. And here's what it says. It says that it's equal to 1 over n plus 1 times u to the n plus 1, and then I think it says plus c. Well, why do we have the c there? In case there was a constant. So technically, my answer up here should have been 1/5 x to the 5th plus c. I just put a plus c there to represent the constant that could have been there. Later on, we'll learn how I could actually find out what that constant is using differential equations. Okay? But for now, all you need to know is add 1 to this and put 1 over it. And that gives me the antiderivative of a basic monomial. All right? So if I wanted... let me come back to the constant idea, because we need to put this in notes. Why the c? Why the c? Well, think of this. F of x, let's say my original function was 6x squared plus 7. Right? My original function was 6x squared plus 7. What's the derivative of it? Isn't it just 12x? Didn't the constant go away? So if I integrate and go backwards, all right, if I integrated the 12x dx, okay, What is the antiderivative of it? Well, I told you it would be x squared times 1 over 2, but then you still have this 12, so it's times 12. So what do you get? You still get 6x squared. But guess what? My original function that I started with had this plus 7. Well, if I'm just integrating plain old 12x dx, I have to account for the fact that there could have been a constant out there. So I just write plus c. Later on, we will find out how to find that c. But to know that, we have to have more information than what I just gave you. Okay? So if here's the key thing that you need to understand. If this is an indefinite integral, indefinite answers must have plus c. Because I don't know if there was a constant there or not. Okay? Because the 12 was already there. And I'm going to talk about that as we learn some of these rules of integration. Let's keep moving here and you'll see how that works. Let's get to several examples now. Let's say that I have the integral of 1 over x cubed dx. Okay? Well, first things first, I've taught you never leave that thing written that way. Write it as a negative exponent, x to the negative third dx. Okay? Well, follow the rule that I just told you. Add 1 to the negative 3. What is it? So this will be x to the negative 2 times 1 over negative 2. There you go. Problem's done, but I need to put plus c. Now, could I write that a little bit better? I think we could. I think we could write this as 1 over negative 2x squared plus c. I think that's a little bit better looking answer. All right? Now, the next thing you need to see is the question that was asked a minute ago with constants. Watch this theorem. If I have the integral of c times a function, all you have to do is integrate normally. Okay? Integrate normally and then multiply your answer by c. That's all you have to do. Kind of like what we did with derivatives. So for example, if I had the integral of 7x squared dx, all I have to do is pull the 7 out in front. 7 times the integral of x squared dx. And find the antiderivative, and then multiply it by 7. So isn't this going to be x cubed times 1/3? And then I have to just multiply it by 7. So it would be 7/3 x cubed plus c. Okay? Now, real quick, before we run out of time, these are on your integral table. But real quick, let's think, how about this one? What's the integral of cosine? Think backwards. What do I take the derivative of to get cosine? Isn't it sine? So this is sine x plus c. Okay? What's the integral of sine x dx? Now this one you have to think a little bit more. It would be negative cosine of x, right? It would be negative cosine of x plus c. And tonight you're going to have some that you may need to simplify first. Like this one. The integral of tangent over secant x. If you get one like this one is not on the integral table. So you need to simplify first. How would I simplify it? Using what I know about trig functions. Isn't tangent sine over cosine? And isn't secant 1 over cosine? And you multiply by the reciprocal, sine over cosine times cosine over 1. Those go away, and now I'm just integrating sine x dx, which is negative cosine x plus c. And the only other thing that I want to point out before you leave is, what if the integral has a couple terms? What if the function has a couple terms? You can break it up. I can make this the integral of 5x cubed plus the integral of 2 cosine x and do them separately. Okay? And we are going to stop there for today.